You have already felt it. End. There is a moment, somewhere between deciding to sleep and actually sleeping, where your body just goes. Not gradually, not through stages you can track from the inside. One moment you are still holding the small leftover weight of the day, the thought you didn't finish, the glass you meant to put away, and then that weight is simply no longer being held by anyone. Something released it. Or you stopped being the kind of thing that could hold it. This is where we begin. Not with outer space, not with equations written on a blackboard that no one erases. Here, in the specific physics of lying down. You have been fighting gravity your entire waking life, and nobody told you that was what you were doing. Every muscle that holds your spine upright, every adjustment your legs make when you shift your weight, every tiny correction your neck performs 40 times an hour to keep your head from dropping forward, all of that is labor. Continuous, automatic, invisible labor directed entirely at resisting the one force in the universe that never takes a break, never loses interest, never looks away. And you do this without thinking about it, the way you breathe without thinking about it, the way your heart continues without being asked. Your body learned gravity before it learned language, before it learned faces. You were a few weeks old, still soft in ways you have no memory of, and already your nervous system was beginning the long negotiation with a force it would never fully win. Gravity pulls on you at roughly 9.8 meters per second, squared at the surface of this planet. That number is specific to here, to the particular mass of the Earth beneath you, and the particular distance between you and its center. On the Moon, it would be about 1/6 of that. On Jupiter, it would be more than twice as much. On a neutron star, if such a landing were survivable in any sense, the number would be so large the concept of standing would dissolve entirely. But here, tonight, it is 9.8. And your mattress is pushing back against it with exactly enough force to keep you from going anywhere, and for a few hours the contest is suspended. That suspension is worth sitting with for a moment. When you sleep on your back, your spine decompresses. The discs between your vertebrae, which spend the day slowly being compressed by the weight of everything above them, gently re-expand during the night. You are, in a very precise sense, slightly taller when you wake up than when you went to bed. Not by much. A centimeter, roughly. Astronauts in microgravity, free from the constant compression of Earth's pull, gain several centimeters in height over the course of a long mission, and they have to readjust when they return. Your body has a shape that is the result of being here, in this gravity, on this surface, and when that gravity is partially relieved, even for 8 hours, the shape slowly begins to remember something else. None of this is unusual. None of this is dramatic. It happens every night to everyone, and it goes entirely unnoticed because there is nothing to notice. You just feel lighter in the morning sometimes, if you notice it at all. But there is something quietly strange about the fact that the force responsible for all of this, the force that has been shaping your spine since before you could walk, the force that required your entire muscular system to evolve in direct response to it, is the weakest force in nature by an almost incomprehensible margin. Not slightly weaker, not considerably weaker. Weaker by a factor that would take most of this paragraph to write out in full. The electromagnetic force, which is the force responsible for almost everything you interact with directly. The push of your chair against your body, the tension in your muscles, the signal travelling down your optic nerve right now, is somewhere in the range of 10 to the 36th times stronger than gravity. That is a 1 followed by 36 zeros. If you tried to imagine a physical comparison, you would run out of useful objects before you got close to the ratio. The sun, the distance from here to the nearest star, the number of atoms in your body, none of these give you enough room to express how much weaker gravity is than electromagnetism. And yet, you feel gravity constantly. You have never once directly felt the electromagnetic force as a unified thing. You feel its effects, the solidity of surfaces, the warmth of absorbed light, the resistance of materials, but not the force itself pulling on your body the way gravity pulls on your body. Gravity is the thing you wake up to. Gravity is the thing your muscles exist to argue with. Gravity is the reason you get tired. The weakest force in the universe is the most present force in your life. That is where this begins, not with an explanation, with a strangeness that has no resolution yet. Just the fact of it, sitting here, the way the room sits around you at this hour, quietly present, not asking anything. The chapter does not know why gravity is this weak. Nobody does. That is not a temporary gap. That is the current state of human knowledge about one of the 4 fundamental forces of nature. The weakness is real, precisely measured, universally observed, and almost completely unexplained. But that comes later. For now, the ceiling above you, the floor below, the mattress holding you at exactly the right distance from both. The gentle, relentless, embarrassingly feeble force keeping everything exactly where it is. You fought it all day. You didn't notice you were doing it. Now you've stopped. And the physics of your spine is very quietly undoing 8 hours of compression, while you go wherever it is you go when you sleep. That's enough for now. Let that be enough. 3 forces walked into a room. The paperclip is already in the air. A small magnet, the kind you'd find on a refrigerator, the kind that costs almost nothing and holds up a photograph, is holding a steel paperclip suspended against the full gravitational claim of the Earth. 6 sextillion metric tons of planet pulling downward on a few grams of metal, and a thumbnail-sized piece of magnetized iron is winning. Not straining, winning comfortably. The paperclip hangs there as if gravity had simply not been consulted. This is not a trick. It is a demonstration of a ratio so extreme that the word ratio doesn't quite cover it. There are 4 fundamental forces in nature. They go by several names depending on who is doing the describing, but the useful versions are these: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These 4 forces account for every physical interaction in the observable universe. Every collision, every bond, every decay, every orbit, every thought your brain produces at this moment, all of it is one or more of these 4 forces doing their work. Nothing else is needed. Nothing else exists in the inventory. They are not equal. Gravity pulls every object with mass toward every other object with mass. It acts across any distance. It cannot be blocked or shielded. You cannot stand between 2 objects and deflect their gravitational attraction the way you might stand between 2 magnets and interrupt their field. Gravity passes through everything. It reaches across the space between galaxies and still applies, still pulls, still curves the paths of things that are moving. It is, in this sense, the most universal of the four forces. Nothing with mass escapes it. Nothing with energy escapes it. Light bends around massive objects because space-time is curved by mass, and light follows the shape of space-time the way water follows the shape of a bowl, and it is, by an enormous margin, the weakest of the four. Electromagnetism is what holds atoms together into molecules. It is what makes your chair solid. Not the atoms themselves, but the electromagnetic repulsion between electron clouds that prevents matter from simply passing through other matter. It governs how light is produced and absorbed and reflected. It is what your nervous system runs on. It is the force behind every chemical reaction, which means it is the force behind every biological process, which means it is, in a very direct sense, what you're made of at the operational level. A magnet holding a paperclip against Earth's gravity is almost insultingly easy work for electromagnetism. The force barely notices. The strong nuclear force is stranger and more localized. It acts only across distances roughly the size of an atomic nucleus, which is to say distances so small that the word small stops conveying anything useful. Inside that range, it is the most powerful force we know. It binds protons and neutrons together against the electromagnetic repulsion that would otherwise blow every nucleus apart. Protons carry positive charge, and positive charges repel each other, which means every atomic nucleus above hydrogen should immediately explode. And the reason they don't is that the strong force is holding them together with a grip that makes electromagnetism look casual. It does not reach beyond the nucleus, but inside the nucleus, nothing touches it. The weak nuclear force is the hardest to visualize because it does not pull or push in the way the others do. It transforms. It changes one type of particle into another. It is responsible for a specific kind of radioactive decay. The kind where a neutron inside a nucleus converts into a proton and releases a fast electron and a neutrino in the process. This conversion is what makes certain isotopes unstable. It is part of what makes the sun burn the way it burns. The weak force mediates the process by which hydrogen nuclei fuse into helium, and without it, the chain reaction that powers every star would not proceed. The weak force does not hold things, it changes them. So, a force that holds the universe together across any distance, feeble beyond imagining, a force that shapes all matter and drives all chemistry, enormously powerful at human scales, a force that binds the nucleus with a grip nothing else approaches, invisible beyond its tiny range, a force that quietly transforms particles from one thing into another, powering stars from the inside. 4 forces. One of them is gravity. Physicists have been trying, with increasing urgency, to understand why the 4 forces have the strength they have. The question sounds like it might have a tidy answer. It does not. The strong force is strong by a factor we can calculate precisely, but cannot fully derive from deeper principles. The electromagnetic force has a specific coupling constant, a number describing how strongly it acts, and that number is what it is, and the universe would be nearly unrecognizable if it were even slightly different. But nobody can tell you, from first principles, why it has that value rather than some other value. These are known problems in physics. They are not embarrassing ones. They are hard ones. But gravity's weakness is something else. The gap between gravity and the other forces is not a gap the way the gap between a bicycle and a sports car is a gap. It is a gap the way the gap between a bicycle and the speed of light is a gap. And the fact that gravity is the force you feel most directly, the force that shaped your skeleton, that keeps the atmosphere from drifting away, that holds the planets in their paths, that controls the large-scale structure of the entire observable universe, while simultaneously being almost uselessly weak at the scale where the other forces do their work. That fact sits at the center of a problem physicists call, with characteristic understatement, the hierarchy problem. We will get there. The problem needs room. It will get it. For now, the paperclip, still hanging. The magnet still holding it against the full weight of the earth, doing it without effort, without any obvious reason why one small patch of magnetized iron should win so easily against the planet. The contest is not even close. It has never been close. The paperclip does not know it is supposed to be impressed by the scale of what it is resisting. Gravity has been pulling on it the whole time. It just keeps losing. The field that is almost nothing start at the number, not an approximation. The actual number that describes how weakly gravity couples to the particles it acts on, relative to the other forces. It is written as a dimensionless ratio. It compares gravity to electromagnetism, and the ratio is approximately 1 × 10 to the negative 36th power. That is 0 point and the 1. Write it on paper. Actually try it. You will run out of patience somewhere around 0:12 and have to count back to make sure you haven't miscounted. That experience, the tedium of the counting, the way the number stretches past the point where it holds meaning, is more accurate than any analogy. Now try to build an analogy anyway. If you gave the electromagnetic force the height of the Burj Khalifa, the tallest building on Earth at around 828 meters, then gravity would be given a height proportional to that ratio. You would need to express gravity's height in units of meters divided by 10 to the 36th. That is not a height. That is smaller than any physical object that exists. It is smaller than a proton by many orders of magnitude. There is no object you can point to and say, gravity is that small compared to electromagnetism. The comparison exceeds the physical world's ability to illustrate it. So the number just sits there, precise, real, measured to high accuracy, and almost completely opaque. Here is where I should say something clarifying. Here is where a voice that fully understood this would offer the next logical step, the reason, the framework that makes the number less strange. I don't have that. Nobody does exactly. There are candidate explanations. We will get to them. But none of them is settled, none of them is confirmed, and the number itself remains for now an observed fact in search of a cause. Which is a strange position for physics to be in. Physics is extremely good at deriving things. Given the right framework, it can tell you the magnetic moment of an electron to 11 decimal places and have experiments confirm it to 11 decimal places. That level of precision is almost unsettling. It suggests a deep order underneath everything, and yet the most basic ratio between 2 of the 4 fundamental forces, a ratio you could measure with a compass and a paperclip, remains unexplained at the level of principle. The number 10 to the negative 36 was not derived. It was found. That distinction matters more than it might seem. Most of the other constants in physics carry at least a partial theoretical story. They fit into frameworks in ways that, if not fully explanatory, at least feel constrained. The fine structure constant, which governs the strength of electromagnetism, appears naturally in quantum electrodynamics. The masses of the fundamental particles, strange and varied as they are, slot into the equations of the Standard Model in ways that are at least internally consistent. Gravity's coupling strength does not slot in anywhere comfortably. It sits outside the Standard Model entirely. General relativity describes gravity beautifully and completely at large scales, and quantum field theory describes the other three forces beautifully and completely at small scales. And the two frameworks do not agree about gravity's strength in the regime where they should overlap. This is the part that goes quiet if you sit with it. The two best theories in physics, the two most tested, most precise, most empirically verified descriptions of reality humanity has ever produced, give incompatible descriptions of gravity at high energies. Not subtly incompatible, catastrophically incompatible. When you try to apply the tools of quantum field theory to gravity, the equations produce infinities that cannot be renormalized the way they can for the other forces. The math breaks. Not in an interesting way, in a way that suggests something is deeply missing. What is missing is not known. The number 10 to the negative 36 is real. The breakdown of the math is real. The gap between the two frameworks is real. And for now, all three facts exist without a single story that connects them. That feels like where this chapter should stop. Not because there is nothing more to say, because this is the place where the ground goes uncertain. Not dramatically. The way ground goes uncertain in fog. You're still standing. You just cannot see exactly what you're standing on. The number is still there. Written out, it is almost nothing. And somehow, almost nothing is what holds all of this together. What the planet is actually doing to you begin far out. Not metaphorically, literally far. Far enough that the Earth is a small bright disk against a field of nothing, the way it looks in photographs taken from the outer solar system, small enough to cover with a fingernail, its atmosphere invisible at this distance, its oceans indistinguishable from its land. From here the planet looks inert, a rock, a pale blue point that happens to have a moon. Nothing about it suggests the thing it is doing to the space around it, the thing it has been doing continuously since it formed, the thing it is doing to you right now. Come closer, closer still. The disk becomes a sphere. The sphere develops texture, clouds, coastlines, the slow curve of the Terminator line between day and night. Still nothing in the visual field suggests what is happening geometrically. The planet does not look like it is doing anything. It looks like it is just sitting there, which is, in a specific and important sense, exactly the problem with the rubber sheet. You have probably seen the rubber sheet. It appears in almost every popular explanation of general relativity. A flat elastic surface, a heavy ball placed in the center, the surface deforming downward around the ball into a depression, smaller balls rolling toward the depression not because they are pulled, but because they are following the curve of the surface. The image is everywhere. It has been used in documentaries, in textbooks, in museum exhibits, in countless hours of science communication. It is also, in one crucial respect, misleading in a way that matters. The rubber sheet is a two-dimensional surface curving into a third dimension that you can see. The gravity that pulls the smaller balls toward the depression in the rubber sheet is the gravity you're trying to explain. The analogy uses the thing it is explaining to demonstrate itself. It works visually. It fails conceptually. What general relativity actually describes is not a two-dimensional surface curving into a visible third dimension. It is four-dimensional space-time, 3 dimensions of space and 1 of time, curving in a way that has no external dimension to curve into, no higher dimensional space that the curve is visible from. The curvature is intrinsic. It is a property of the geometry itself, not a visible deformation from outside. This is the part where most explanations either push through with the rubber sheet anyway, or reach for different analogies that fail in different ways. Neither option is fully satisfying, which is itself information about the idea. Some things in physics genuinely resist being pictured, and general relativity's description of gravity is one of them. Not because it is beyond understanding, but because the kind of understanding it requires is mathematical rather than visual, and mathematical understanding does not translate cleanly into images. What translates is this: the presence of mass changes the geometry of space-time in the region around it, and that change in geometry affects the path that objects take through that region. Objects do not experience a force pulling them toward the massive object. They move along the straightest possible path through a geometry that the massive object has curved. What looks like a force is a geometric effect. What feels like being pulled downward is the consequence of following a straight line through curved space-time, where the straight line happens to end at the surface of the planet. This is not a metaphor. This is what is actually happening. The reason it feels like a pull is that your body is being prevented from following its natural path. Your natural path, in the absence of the Earth's surface beneath you, would be to fall, to follow the curve of space-time inward toward the planet's center. The ground is what stops you. The force you feel when you stand on a surface is not gravity pulling you down. It is the surface pushing you up, accelerating you away from the path you would otherwise take. Gravity, in general relativity, is not a force at all in the traditional sense. It is the shape of the space you are moving through, and the shape is being made by the mass of everything around you, all the time, continuously, at a speed that is also the speed of light. Changes in the gravitational field when mass moves or accelerates propagate outward at the speed of light. If the sun were somehow to vanish at this exact moment, the Earth would not immediately fly off in a straight line. It would continue in its orbit for approximately 8 minutes, because that is how long it takes for the absence of the sun's gravitational influence to travel the distance between them. For 8 minutes the Earth would orbit a sun that was no longer there. Then the geometry would change, and the Earth would come closer still, back down through the atmosphere, back to the surface, back to the specific room where you are, back to the mattress, the ceiling, the specific weight of being horizontal. The planet beneath you is curving space-time right now, continuously. The curve extends outward in all directions, growing weaker with distance but never reaching zero, never stopping, rolling out at the speed of light in every direction simultaneously. You're sitting inside a geometric distortion produced by 6 sextillion metric tons of rock and metal and ocean. You cannot feel the geometry directly. You can only feel the surface that is stopping you from following it. Down, A few words, quiet. That is all this needs now. The ground pushes, you stay. The geometry continues without you. Somewhere the signal is arriving. Late right now. From somewhere in the universe, something is headed here. Not metaphorically, not as a thought experiment. Right now, at this moment, gravitational waves produced by events that happened before complex life existed on this planet are passing through the room you're in, through the walls, through the floor, through you. They have been travelling for millions or billions of years, and they will continue travelling after they pass through you. Changed by nothing, absorbed by nothing, reduced by nothing except the natural spreading of a wave front across an ever-increasing sphere of space. You cannot feel them. No human body is sensitive enough, but they are here. The detection of gravitational waves is one of the stranger achievements in the history of science, and it is strange in a specific way that is easy to miss if the story gets told too quickly. The strangeness is not that we detected them. The strangeness is what we had to build to do it, and what that thing had to be sensitive to. LIGO, the Laser Interferometer, Gravitational Wave Observatory, consists of two L-shaped detectors, one in Louisiana and one in Washington State, each with arms 4 kilometers long. A laser beam is split and sent down both arms, reflects off mirrors at the ends, and returns to a detector. If the two arms are exactly the same length, the returning beams cancel each other out in a specific way. If something changes the relative length of the arms, even by an amount far smaller than the diameter of a proton, the cancellation shifts and the detector registers it. The change that LIGO is designed to detect, on the order of 10 to the negative 18 meters, 1,000th the diameter of a proton, across an arm 4 kilometers long. Take a moment with that. Not the number itself, but what it means to build something that can notice it. The mirrors at the ends of the arms weigh 40 kilograms each. They hang from chains of pendulum specifically designed to isolate them from ground vibration. The vacuum inside the tubes is maintained at a pressure lower than the surface of the moon. The entire system is designed to exclude every possible source of physical noise, seismic activity, thermal fluctuation, air pressure changes, the vibration of passing trucks, the acoustic effect of wind, so that when the detector registers something, the only remaining candidate is something that passes through all of that insulation without being stopped. Gravitational waves pass through all of it without being stopped. On September 14th, 2015, at 5:51 in the morning Eastern Time, both detectors registered a signal. Louisiana first. Washington State 7 milliseconds later. The 7 milliseconds corresponding exactly to the time it takes a wave travelling at the speed of a light to cross the distance between them. The signal lasted 1/5 of a second. Its shape, the way its frequency and amplitude changed over that 1/5 of a second, matched exactly the pattern that general relativity predicts for two black holes spiralling inward toward each other and merging. The black holes involved had masses of approximately 29 and 36 times the mass of the Sun. When they merged, approximately 3 solar masses worth of energy was released as gravitational waves in a fraction of a second. That event happened approximately 1.3 billion years ago, when the most complex life on Earth was still single-celled organisms drifting in shallow seas. The signal that LIGO detected was the end of a billion-year journey. The wavefront that passed through Louisiana and then Washington state on that September morning had been travelling since before the Cambrian explosion, since before multicellular life, since before anything with a nervous system had ever existed on this planet. It had passed through every galaxy cluster between here and there, curved slightly around every massive object it encountered, and arrived here carrying a precise record of the event that produced it, a record written in the shape of space-time itself, in a language that only exists in the geometry of how distances change over time. The detection lasted 1/5 of a second. The signal swept upward in frequency, a chirp, a sound that physicists played through speakers after converting the wave pattern to audio. It sounds like a very brief low rumble rising to a slightly higher pitch. It sounds like almost nothing. It is one of the most information-rich signals ever detected by any instrument humans have built. In that 1/5 of a second, the detector was reading geometry, actual changes in the shape of space, changes produced by a collision of incomprehensible violence, so far away and so long ago that the violence itself is entirely unreachable, existing now only as a pattern in the curvature of the space it passed through on its way here. LIGO has since detected dozens more events: black hole mergers, neutron star mergers, collisions between objects whose nature is still being worked out. Each signal is different in its details. Each one is a record. Each one has been travelling for a specific amount of time, from a specific distance, and each one passed through you at some point, registered nothing on your nervous system, and continued outward. Gravity carries information. It does this very quietly. It does it across distances and time spans that are difficult to think about directly without the mind sliding off towards something more manageable. And it does it despite being the weakest force, precisely because it cannot be shielded, cannot be absorbed, cannot be stopped by anything. Electromagnetism carries information too, but light can be blocked. Gravitational waves pass through the Earth as if the Earth were not there. Something is still arriving, right now, from somewhere. The detectors are running. The mirrors are hanging in their vacuum chambers, isolated from everything except the thing that cannot be isolated from. And some pattern in the geometry of space produced by something that happened before this planet existed is somewhere between its source and here, carrying its record patiently across the dark, not knowing it is being waited for, not knowing it is arriving at a moment when something on a small rocky planet has finally built something sensitive enough to notice. The signal does not know what it means. Only we do. And even we are still figuring out what to do with that. The hierarchy, or why physicists lose sleep. You already know the answer to this one. That is what the brain does with a familiar number. It files it. It says, yes, gravity is weak, understood, moving on. The familiarity is the problem. Because the moment you slow down and actually look at what the weakness means, not the number itself, but the implications of the number, the places it leads when you follow it seriously, the answer stops feeling known and starts feeling like a door that was always there and you never tried the handle. So, slow down. The hierarchy problem is this: the Higgs field, which gives mass to fundamental particles, has a natural energy scale associated with it. Without any additional physics beyond what we currently know, quantum corrections, small contributions from virtual particles flickering in and out of existence, should drive the mass of the Higgs boson up to an enormously high energy scale called the Planck scale. The Planck scale is where gravity and quantum mechanics are expected to become comparable in strength, where the weakness of gravity finally closes the gap. It sits at approximately 10 to the 19 giga-electron-volts. The actual measured mass of the Higgs boson is about 125 giga-electron-volts. The discrepancy between where the Higgs mass should naturally land and where it actually sits is a factor of roughly 10 to the 17th. That gap is the hierarchy problem. It is the same gap seen from a different angle as the weakness of gravity. The question of why gravity is so weak and the question of why the Higgs mass is so much lower than expected are, at their root, the same question wearing different clothes. Physics does not like coincidences of this magnitude. When a number in a physical theory is enormously different from what the theory's natural scales would suggest, physicists call this fine-tuning, and fine-tuning is treated as a symptom that something is missing from the theory, a symptom that the framework being used is incomplete in a way that is producing an apparent coincidence where there should be an explanation. The history of physics contains several examples of apparent fine-tuning that turned out to be resolved by deeper physics. The smallness of the cosmological constant was once thought to be fine-tuned until it was partially recontextualized. The stability of the proton seemed fine-tuned until the strong force was better understood. The hierarchy problem has been waiting for its resolution for decades. It has not arrived. Two candidate solutions have dominated the conversation, and both of them are worth sitting with, not because either is confirmed, but because of what each one implies about the structure of reality. The first is supersymmetry. Supersymmetry proposes that every particle in the Standard Model has a partner particle, a superpartner, with slightly different properties. Fermions, the matter particles, have bosonic superpartners. Bosons, the force-carrying particles, have fermionic superpartners. If supersymmetry is correct, these superpartners exist and contribute their own quantum corrections to the Higgs mass, and the contributions from the superpartners would cancel out the contributions from the regular particles, stabilizing the Higgs mass at a natural value without requiring any fine-tuning. The hierarchy problem would dissolve. The gap between the Higgs mass and the Planck scale would be explained not by coincidence, but by a symmetry that keeps the corrections in check. Supersymmetry is elegant. It also makes predictions. The superpartners should be detectable at high enough energies. The Large Hadron Collider has been running at energies where the lightest superpartners were expected to appear, and they have not appeared. This does not rule out supersymmetry entirely. The superpartners could be heavier than current colliders can reach, but it has made the landscape less comfortable for the most straightforward versions of the theory. The absence is not a refutation. It is a pressure. The second candidate sits differently in the imagination. Extra dimensions. The proposal, developed in various forms by several groups of physicists in the late 1990s, is that the apparent weakness of gravity is not a fundamental property but a geometric one. The other three forces are confined to the three spatial dimensions we experience. Gravity is not. Gravity propagates through additional spatial dimensions that are curled up at scales too small to have been directly detected, or in some versions extends into a higher dimensional bulk space that the other forces cannot access. If this is true, then gravity is not actually weak. It is full strength, comparable to the other forces, but most of it is going somewhere we cannot see. What we experience as gravity's weakness is the small fraction of it that happens to be in our dimensional neighbourhood. This is not a metaphor. This is a mathematical proposal with specific testable predictions. If extra dimensions of the right size exist, gravity should deviate from its expected inverse square behaviour at short distances below the size of the extra dimensions. Experiments have tested this by measuring gravitational attraction between small masses at sub-millimetre scales. So far, no deviation has been found down to scales of roughly 50 micrometers. This constrains but does not eliminate the extra dimension hypothesis. The dimensions, if they exist, are smaller than 50 micrometers, or they are structured differently than the simplest models predict, or they are not there. Here is where the orbit completes and comes back. Both solutions, supersymmetry and extra dimensions, are attempts to answer the same question. Why is there a hierarchy? Why is the scale of gravity so different from the scale of everything else? And both solutions, for all their elegance and internal consistency, have so far produced no confirmed experimental signature. The problem that motivated them remains open. The hierarchy is still there. The gap is still unexplained. Physicists have built too sophisticated frameworks to resolve a discomfort that the numbers produce, and the numbers are still producing the discomfort, which means something. It means either the solutions are right and we simply have not yet built experiments sensitive enough to find them, or the solutions are wrong and the real answer is something nobody has thought of yet, or, and this is the option that sits most quietly in the back of the conversation, the hierarchy is not a problem to be solved. It is just a fact about the universe, a fact with no explanation deeper than itself, a coincidence that is simply true. Physics tends to resist this last option. The history of the discipline is largely a history of apparent coincidences turning out to be explained by deeper structure. The position of the Earth in the solar system looked coincidentally perfect for life, until it became clear that life arises where conditions permit, and does not arise where they do not. The apparent fine-tuning of physical constants looks coincidental, until you consider that observers can only exist in universes compatible with observers. These are not full resolutions of the fine-tuning problem, but they are moves that change what the problem requires. The hierarchy problem may have a move like that waiting somewhere, or it may not. For now, it orbits. The question goes around the same point from different angles and does not land. Every approach that gets close enough to feel like an answer turns out to be a different version of the question. The gap between gravity and everything else is still there, measured precisely, unexplained cleanly, sitting at the centre of theoretical physics like something left on a table that everyone keeps walking past and nobody picks up. It has been there for a while. It is not going anywhere. Thin places begin inside the wall, not the wall of the room, the wall between here and somewhere else, a boundary so thin it has no thickness in any conventional sense, a surface that is not a surface, a division between a space you can move through and a space that your entire body, every instrument you have ever built, every photon you have ever detected, has never entered and may never enter. It might be right there. The proposal is geometric. It starts with a question about where gravity goes. If gravity is produced here, by mass here, acting on matter here, then why is so little of it arriving? The other forces fill the space they act in completely. Electromagnetism between two charges does not lose most of itself somewhere on the way. The strong force inside a nucleus does not leak. But gravity, as measured, is weaker than any natural calculation suggests it should be by that number with 36 zeros. Something is happening to it. Or something is happening to the space it travels through. The idea, one version of it, the version proposed by Nima Arkani Hamed, Savas Dimopoulos and Gia Diwali in 1998, known by the initials ADD, is that space has more dimensions than 3. Not in a vague metaphorical sense, in a specific mathematical sense. Additional spatial dimensions, compact and curled, too small to have been directly resolved by any experiment, through which gravity propagates, but through which the other forces do not. The standard model particles and the forces that govern them are confined to a 3-dimensional surface, a brane in the language of string theory, embedded in a higher dimensional space. Gravity is not confined. Gravity leaks into the bulk. Follow the thread. If gravity spreads into extra dimensions, its strength in those dimensions is diluted. The gravity you measure between two masses on a laboratory bench is what remains after most of it has gone somewhere else. The weakness is not intrinsic. It is the result of a distribution. Gravity is full strength somewhere, just not entirely here. This changes what you are standing on. Conceptually, you are on a surface, a brane, a thin slice of the full dimensional space. Everything you can touch, everything that has ever been measured, everything that has ever interacted with anything in any experiment, all of it is on this surface. The stuff of the universe, as far as any instrument has ever determined, does not leave the brain. It cannot. The forces that bind it here confine it here, except gravity. Gravity goes through. The thread goes further. If the extra dimensions are large enough, large meaning anything above the experimental exclusion limit of roughly 50 micrometers for 2 extra dimensions, much smaller for more, then gravity should deviate from its expected inverse square law at those scales. 2 masses brought close enough together should feel a gravitational attraction slightly stronger than the standard calculation predicts, because at that distance the extra dimensions become relevant, and gravity has less room to spread into them. Experiments have looked for this deviation carefully, at scales from millimeters down to tens of micrometers. Nothing found yet. The inverse square law holds to the limits of what has been tested, which means the extra dimensions, if they exist, are smaller than what has been tested, or structured differently, or the theory is wrong in its simplest form and the correct version is more subtle. All of these remain open. Here is where I am not certain what to do with the idea, and I want to say that plainly rather than paper over it with confidence I do not have. The proposal is mathematically consistent. It makes genuine predictions. The predictions have not been confirmed, but they have not been fully excluded either. It exists in a region of physics where the theoretical machinery is sophisticated and the experimental access is limited by what we can currently build, and that region is uncomfortable because it is genuinely hard to know how much weight to give an unconfirmed but unfalsified theory. Physics has elegant wrong theories and ugly right ones, and very few reliable ways to tell the difference before the experiment. What I am more certain about is the image, not the image as illustration. The image as a way of holding the problem. Something is going somewhere we cannot follow. The gravity that should be here, by every natural calculation, is not entirely here. Where it goes, if it goes anywhere, is a space that is either too small to have been reached by any probe, or simply not accessible from inside the brain. We are in a room, and the room has a wall, and we cannot see the other side of the wall, and we are not even certain the wall exists in the way we are imagining it. But the gravity is still weak. That part is not uncertain, and the thread, followed to its end, arrives at the same place every time. Something is missing from the inventory of what this space contains, or something is missing from the inventory of what this space is. Either the mass is somewhere we cannot see it, or the dimensions are somewhere we cannot reach them, or the weakness is a fundamental property with no geometric explanation at all. The thread ends there, at a place where 3 doors stand and none of them have opened yet. The thing that holds galaxies together is not gravity. The galaxy is already rotating when this chapter finds it. A spiral galaxy, face on, arms curving outward from a bright central bulge, stars distributed across a disk that spans tens of thousands of light years. It is rotating. Every star in it is orbiting the galactic center, the way the planets orbit the sun, the way the moon orbits the Earth. This is not unusual. This is what galaxies do. What is unusual is the speed at which the outer stars are orbiting. In a solar system, the planets farther from the sun move more slowly than the planets closer to it. This follows directly from the physics. The sun contains nearly all the mass of the solar system. Its gravitational influence decreases with distance, and objects at greater distances need less orbital speed to maintain a stable orbit against that weaker pull. Mercury moves fast. Neptune moves slowly. The relationship between distance and orbital speed follows a predictable curve called the Keplerian rotation curve, and it slopes downward as you move outward from the central mass. This is not a guess, it is derivation. It follows from gravity and from where the mass is. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford measured the rotation curves of spiral galaxies. They expected to find the Keplerian pattern, fast in the center, slower toward the edges, the curve dropping off as distance from the galactic center increased. What they found was different. The outer stars of spiral galaxies were moving at roughly the same speed as the inner stars. The rotation curve was flat, not sloping, flat. The speed did not decrease with distance the way it should have if most of the mass were concentrated in the visible center. For the rotation curve to be flat, there had to be more mass, much more. Mass distributed in a large halo surrounding and extending well beyond the visible disk of the galaxy, in quantities large enough to keep the outer stars moving at the speeds they were observed to be moving. The math was unambiguous. Either the mass was there in some form, or the law of gravity was behaving differently at galactic scales than it behaves in the solar system. Most physicists landed on the first option. The mass is there, it is just not visible. Dark matter does not emit light. It does not absorb light. It does not interact with the electromagnetic force in any way that has been detected. It interacts gravitationally. It has to, because its gravitational effect is what we are measuring. And it may interact through the weak nuclear force, though this has not been confirmed. Everything else about it is unknown. Its composition is unknown. Whether it consists of one type of particle or several is unknown. Whether it is particle at all in the conventional sense or some other form of matter is unknown. What is known is this: the universe contains approximately 5 times as much dark matter as ordinary matter. The atoms, the protons and neutrons and electrons, the stuff that makes up stars and planets and your body and every instrument ever built, all of that is roughly 20% of the matter in the universe. The other 80% is dark, present only through its gravitational effect, known only through the force that is weakest, that cannot be shielded, that passes through everything, including whatever dark matter is. We mapped the large-scale structure of the universe using light. Galaxies glow. Galaxy clusters glow. The cosmic microwave background, the oldest light in the universe, carries information about the structure of the early cosmos in the pattern of its temperature fluctuations. All of that mapping was done with electromagnetism, with photons, with the force that dominates chemistry and biology and every technology we have. And what the map revealed is that the luminous structure, the part that glows, is scaffolded by something that does not glow. The visible universe is tracing the outline of an invisible structure. The galaxies sit where dark matter concentrations allowed gas to collapse and stars to form. The galaxy clusters sit at the intersections of dark matter filaments. The large-scale web of the universe is a dark matter web that the visible matter is embedded in. The whole map, in other words, is mostly a map of something we have never directly detected. Only gravity told us it was there. Only gravity, the weakest of the 4 forces, the one that leaks, the one that barely functions at the scale of cells, the one that cannot be shielded or interrupted or explained at a fundamental level. Only that force reaches across the gap between ordinary matter and whatever dark matter is, and tells us something is there, and tells us roughly where it is, and tells us how much of it there seems to be. Every other probe we have is silent. Dark matter does not ring when struck. It does not glow when heated. It does not deflect when a charged particle passes through it. It sits in the data as an absence, a mass without a signal, a weight without a substance, a presence known entirely through the most tenuous of the 4 forces. The galaxy is still rotating, the outer stars still moving at speeds the visible mass cannot account for. Something holds them there, something that has been in the universe longer than the stars, that formed the structures the stars later grew inside, that outweighs all the glowing matter in the cosmos by a factor of 5, that has never once been directly caught. Gravity found it, or at least gravity found its shadow, the shape of what it leaves behind in the paths of the things that glow. That is not nothing. That is, in fact, almost everything we know. A long time from now, nothing will be pulling on anything. Something has already ended. Not here. Not yet. But the ending has begun in the way that very slow things begin. Not with an event, not with a moment you could point to, but with a direction, a tendency, a universe that has been expanding since the first fraction of the first second of its existence, and that sometime in the last few billion years stopped decelerating and began to accelerate. The expansion is not just continuing, it is speeding up. Whatever is driving that acceleration, physicists call it dark energy, which is a name for an unknown thing dressed up to sound like a known one, is winning against gravity, and it has been winning for longer than the Earth has existed, and the margin of its victory is growing. This is where the thread begins, at a universe already in the process of coming apart, slowly, gracefully, without drama. Follow it forward. The first thing to go is proximity, not immediately. On cosmological timescales, which are timescales that make the current age of the universe look like an afternoon, the galaxies that are not gravitationally bound to each other will recede. They are already receding. The light from distant galaxies is already redshifted, stretched toward longer wavelengths by the expansion of the space it travels through, and the farther away a galaxy is, the faster it appears to be receding, not because it is moving through space at that speed, but because the space between here and there is growing. At distances beyond a certain threshold, galaxies are receding faster than light can cross the growing gap between us. They are not moving faster than light. Space itself is expanding faster than light can traverse it. Those galaxies are already, in a practical sense, beyond reach. Their light will never arrive here. They have crossed a horizon. Over time, more galaxies will cross that horizon. The local group, the cluster of galaxies that includes the Milky Way and Andromeda and a few dozen smaller companions, is gravitationally bound. It will hold together. Andromeda and the Milky Way are actually approaching each other and will merge in roughly 4 to 5 billion years, a collision that will be slow and diffuse and will produce not destruction, but a new, larger elliptical galaxy. The local group will remain intact for a very long time, but everything beyond it will recede past the horizon and the night sky will gradually empty. Not in any human lifetime, not in any lifetime that could be imagined by analogy to human experience, but the direction is set, the horizon is moving, the universe visible from here is shrinking. This is what dark energy does to gravity's project. Gravity's project, if it can be called that, has been aggregation, pulling things together. Gas clouds collapsing into stars, stars clustering into galaxies, galaxies drawing together into clusters. The large-scale structure of the universe, that dark matter web with its filaments and nodes, is gravity's accumulated work over 13 billion years. It is a structure built by the weakest force, slowly, patiently, across distances so large that the building took longer than anything else in the universe's history had yet taken, and dark energy is now undoing the outermost layers of that structure, pulling the pieces apart faster than gravity can bridge the gap. The thread goes further. Stars will die. The most massive ones burn fast and are already gone. The sun has roughly 5 billion years remaining on its main sequence. Smaller stars burn cooler and slower and will outlast the sun by enormous factors. Red dwarfs with a fraction of the sun's mass can burn for trillions of years, 100 times the current age of the universe. But they will burn out too, eventually. Star formation itself will slow and stop when the available gas is exhausted and no new supply arrives to replace it. The last star will form and burn and cool and go dark, and the galaxy will become a collection of cold remnants. White dwarfs fading to black. Neutron stars cooling toward the temperature of the surrounding space. black holes accreting what little matter drifts within reach. Then the black holes evaporate. Stephen Hawking showed this in 1974, that quantum effects near the event horizon cause black holes to slowly radiate energy, losing mass over time, over very long times that make the stellar lifetime of red dwarfs look brief. A black hole with the mass of the Sun would take roughly 10 to the 67 years to evaporate completely. A supermassive black hole at a galactic centre might take 10 to the 100 years. These numbers are so large they have no useful analogy. The age of the universe is 10 to the 10 years. The ratio between 10 to the 100 and 10 to the 10 is 10 to the 90, which is itself a number without a useful analogy. But the direction is the same. The black holes too will go slowly, by a quantum process so gradual that calling it evaporation is almost generous. They will diminish. They will reach a final moment. They will be gone. After that, gravity has nothing left to hold. Gravity will still be there. This is the part that stays with you if you let it. Gravity does not stop. It does not turn off when there is nothing left to do. The laws that describe it do not expire. Every cold remnant will still exert a gravitational pull on every other cold remnant across distances so enormous that the pull will be effectively unmeasurable, that nothing will ever come close enough to feel it, that the time required for any two objects to gravitationally interact will exceed any time scale with a name. But the force will be there. The geometry of space-time, shaped by the mass of whatever remains, will still be curved. Gravity will still be doing what it does, just with nothing left to bring together. This is not a sad ending. It does not feel like one if you come at it from the right direction. It is just a shape. The universe has a shape in time the way it has a shape in space, and the temporal shape, followed far enough forward, is one of gradual dispersal, gradual cooling, gradual silence. Gravity built the structure. Dark energy is slowly taking it apart. The building took billions of years, and the taking apart will take incomprehensibly longer. And the force doing the building is the same force that will be the last one still technically operating when there is nothing left to operate on. The weakest force, the most patient one, the one that was already there before the first star lit, that shaped the first structures out of the nearly uniform gas of the early universe, that held together the galaxies where life eventually appeared, that spent every night of every living thing's existence pulling gently on the fluid in its inner ear, reminding it which way was down. It was always weak. It was always patient. It was always, in some sense, that resists being made fully precise, just here, doing what it does, waiting for something to notice.